Right. In this series of slides we're going to use today, we're going to take on an idea which is referred to as measurements. And measurements are a crucial aspect of chemistry. And when you make measurements, you need tools. And obviously, you need the right tool for the right job. And tools for making measurements go back millenniums, as you could see by the artwork of the Egyptians, and of course, the measurements on the moon itself. So, what are the properties of measurements, and what are the tools that are used to make them, and what do you do with the numbers you get? First of all, let's establish this idea. When you have an object, let's say it's the Earth, and you are making observations of this Earth, um, we can make measurements of them. For example, we can state that the Earth has a certain color to it. We can actually assign a wavelength, perhaps, to certain regions of the Earth and the color that comes from there. It has a shape. You could start out by saying, well, it's a sphere, but if you look more closely, it actually is slightly bulging in the middle because of the spin. And you can get more and more precise on the shape, but the shape is a descriptor. It is a attribute of that object. You could also create a weight, and if you wanted to weigh it, you would get a number. You could measure the volume and get a number and a diameter and a surface area. All of those measurements actually are numbers, and those numbers are important because they tell you something about the object. So when you make measurements, it's informing you about the object, but it's not informing you about everything of that object. Now, also realize in science, when we make a measurement, we are restricted to uh, um, values that everybody can agree upon. For example, in general, people could agree upon a certain weight of the Earth. People could agree to a certain amount to the surface area. Now, some people may say, oh, that Earth is pretty, or no, I don't think the Earth is pretty at all. That's a value judgment. And so the word pretty is not a measurement, it's simply a value assigned, or an emotion that's assigned to the object, and actually does not show up then in the scientific world because not everybody can agree upon it. The same as if you see the Earth, perhaps it makes you feel secure. Well, others people may not feel secure by it. But everybody can agree that the shape in general is a sphere, or they could agree that in general there's a certain volume to it. So measurements are what we all can agree upon, whereas these value judgments or emotional statements are valid, they are true, but not associated with a scientific perspective. Now, when we make measurements, there's lots of things about an object we can measure. For example, we can measure the mass of the object. Whether it makes you happy or sad, it's up to you. Now, there's a tool that we use to determine the mass of that object, and of course, you can use a triple beam balance. You can use an analytic balance. These different tools have different level of accuracy, um, and you choose which tool to use, but they're all going to pick up on the same attribute, which is mass. Now, there are basic units that these measurements are made in. For example, in time, you can simply use seconds. Mass, we use grams. Now, it is true the units between different civilizations, like the Egyptians did not use grams, they used some other unit, but they did measure mass just like we do. Um, Distances in the metric system, the basic unit is a meter. Once again, if you go back to the Persian civilization, they measured a property called distance, but they would simply have used a different unit. And so here you see a list of a number of quantities or attributes that you can determine for a given object, and there is a common set of units that are agreed upon in the scientific community called the metric system, and these are the established baseline units that will be used. Now we do have to make conversions, and this was kind of a fun one, in which this is the gallon man. And what the gallon man does, we're not going to use this in chemistry. We don't use it in science at all, but it is kind of a nice illustration of what conversion's all about. And the way the gallon man works is, if you take a look at the center, that's 1 gallon. Think of a gallon of milk. Well, gallon man has 2 arms and 2 legs, and so a quart, 4 quarts will make 1 gallon. Now, each quart, as part of the elbow, is made up of 2 pints. So 2 pints make 1 quart, and 4 quarts make a gallon. And the fingers of gallon man, there are 4 cupped fingers, and those 4 fingers come together to make 2 pints. 2 cups make 1 pint. 2 pints make 1 quart, and you go around all 4 quarts, it will make a gallon. And this was a kind of a fun way of seeing, oh yeah, I got to convert a certain amount of material into smaller units. For example, take a quart and break it into smaller units, which is 2 pints. 2 pints is the same amount of liquid as 1 quart. It's just a different unit container being used. But the problem with the gallon man is these numbers are just ridiculous. How does it 4 cups make 2 pints? Where did that come from? 2 pints make 1 quart? It makes no sense. So this illustrates for us the concept of conversions, but it also illustrates why the English system has a lot of problems with it. I can't move from one value to another very easily. Now, in the metric system, we have a conversion method that's very uniform. Here's what we mean by this. Let's take a attribute or a measurement called length. We call that the base unit. Now, we can measure an object's length, and the length may be less than 1 meter. Well, what we do is not invent a new unit to make it be smaller. We simply take the basic unit and divide it into uniform smaller pieces. And we can say how many of these smaller lengths make up that small object. And so if you were to take a look at the base unit meter, if you divide that, you can shift down to the right. If you divide the unit length meter into 100 smaller units, each of those units, of course, is a centimeter. Now, one thing is, for many of us, we're not used to the metric day to day. So here's a reference point. If you take your pointed finger, that finger you point things at, look at that finger. The width of that is just about 2 centimeters, give or take. So when you start to see measurements in the metric system, when it comes to length, think that the thickness of my pointer finger is 2 centimeters. It gives you a reference point. Now, what happens is the word centi says that it's a small unit of the length called a meter. What if the what's being measured is much larger than a meter? Well, then you have something that is multiples of the meter, and you can get all the way out to a kilometer or a kilometer, and a kilometer is simply 1,000 of these meters laid end to end. So notice that everything is referenced off this basic unit of a meter. And again, a reference point is a kilometer is 0.6 of a mile. I often just work with it as just half a mile. So if you want to always remember that a kilometer is about a half a mile, and the idea of 2 centimeters is the thickness of my finger, you start to get reference points of what these numbers are. So to make the conversion from lengths in meters to kilometer, or I should say to go from kilometers to meter, you can see you're going to multiply by 10, and you divide by 10 to go up. Now, is there another basic unit? Absolutely. There's another unit called volume, and the volume, the basic unit is a liter. Now, we're going to use the same rules, and that's what's kind of cool about the metric system. The same rules of taking your basic measurement unit, in this case liter, or your basic unit length, we're going to always use the same rules if you want to have small units worth of liter or meter, or large amounts of liters or meters. The rules are still the same. So what happens is we can take a liter of soda, and imagine dividing that liter of soda into 1,000 parts. That one part is called a milliliter, and 1,000 of those parts get you back to 1 liter. Now let's get a reference here. How much is 1 milliliter? And the answer is roughly 20 drops of water will occupy 1 milliliter. And so you start to see these numbers, those are nice reference points. Now, of course, you could have a kiloliter, which means you have 1,000 of these liter bottles. Now, here's some reference points as always. A gallon of milk is 3.78 liters. Humans have 5 liters of blood. And if you put a human being into the bathtub or a human being into a pool, it will occupy 70 liters worth of space, average size adult. So notice the same rules are applied to a liter to get these different smaller or bigger units as we did the meter. And that's the big power of the metric system. Again, are we going to need to make conversions in this class? Absolutely. When you go from kilometer and you start to work your way down to the right, kilometer to meters to decimeters, centimeters, millimeter, you're going to multiply the numbers as you move from left to right. And then what you can do is you can divide by these numbers as you move right to left. So that's how you change your units. And we are going to be expected to be able to do that. So if you remember these guidelines, it helps. Now, measure, actually making the measurement. There's all kinds of things that we can use. Notice in this case, we're measuring volume. We can measure volume in what are called volumetric flasks, burette, graduated cylinder, graduated pipettes. All of these are tools, and these tools take care of one thing. They measure volumes of material. In this case, it's a liquid. You would not use a graduated cylinder to measure length any more than you would use a volumetric flask to measure weight. So these are tools specific to a particular item. So volume is an interesting idea. It's the amount of space that an object occupies. And it turns out there are several ways to calculate a volume. One way is called the ruler method, and you simply measure length, height, and width. You multiply them together, and it gives you the volume. But there's a second way to measure the volume of that same object. It's referred to as the water displacement method. And in this case, what you do is you use a volumetric flask, and you fill the flask with water. You always measure it from the bottom of the meniscus. So you measure it there, and you'll notice we have 60 and we have 70, sorry. You have a 60 and a 70. There is no division points between the 60 and 70, but you then estimate the next decimal. So one might suggest that this is approximately 65 milliliters. You could not write down the number any more than that because the instrument won't let you guess better than that. So it's 65 as a starting level. So that's how you make the measurement. So now what we do is we'll take a look at the water displacement process again. In this setup, we would say that there's 20 milliliters of water, again using the same method we had before. So we have 20 mils in this graduated cylinder. We know that because we can measure it. Now what we're going to do is remember, we're trying to solve for the volume of an object. So what we do is we're going to place in the graduated cylinder the object that has that water in it. You want to slide it in, so you put it at an angle and slide it in gently, that way you don't break the bottom. And what you do is you've placed enough water so that once you've slid the object in, it covers the object up. So what happens, as you can see here, is the level 20 has been elevated. So look closely, the water level was 20, and now the water level has been raised to 25. How did that happen? Well, the object that you put in the graduated cylinder displaced or moved the water level up. And so what you do now is you take the difference between the ending volume minus the starting volume, you get 5. Now, couldn't I just take 20 minus 25? Is that the same thing? Yeah, not really. And it's not really because if you do that, you get a negative 5 milliliters. Well, the pennies aren't a negative volume, they're a positive volume. So the rule in this class is whenever you make measurements or a couple of measurements about an object, you take the ending minus the beginning to give you the volume of that object. Now, why exactly do we make these measurements? You make these measurements because they inform you about the object. In this case, these athletes are going to be measured for many things as they carry out their exercise. They're measuring, for example, heart rate. They're measuring the VO2 max, which is the amount of oxygen and CO2 you can take in and expel. They're going to be measuring temperatures. So these measurements are telling you about the human body during times of intense exercise. Now here's an interesting idea for you. If you weigh something, then you know one item, weight. If you know the volume, you know that the object's volume is such and such. But there are some properties of an object that you need two measurements to get the one object. What we're saying here is this. There is a property called density. Well, you may say, oh, that's easy. Get the density instrument out. Well, there isn't one. Why don't I just measure it using the density machine? Because the density requires two machines or two tools to measure two properties, and you put the two properties together to give you the one, which is the density. So the density is two things: the weight or mass of the object and the volume that the object occupies. So when we ask for a number density, the density is 0.56. That 0.56 was not a single measurement by the density machine, which doesn't exist. Instead, it is the mass of the object, which you can measure, divided by the volume of the object, which you can measure. When you put those two together, you now have the property called density. The units, which are very, very important in measurements, the density is given as grams per cubic centimeter or grams per milliliter. And so after any given density number, you would have to include those symbols. So why is the density of an object not the same for every object? And the answer is that the density is a measurement of how tightly packed molecules or atoms are and how heavy the molecules or atoms are that are in that object. And you'll notice it's two things. It's the weight that you can cram inside the box, and it's the volume of the box that you're trying to fill up. As you see here on the left, the items are much more packed in, and the items on the right are much more spread out. And therefore, you would say, if you actually run a calculation, which you will do, you will say, right, the object on the left has a greater density than the object on the right because there's more mass packed into the space available. Let's see here. I always struggle with this. So let's try this.